Dr. Barth, can you hear me?
I have his phone number. Okay.
My brother. It's not really.
There you go. You're on.
Hey guys,
And
I'm here with
I'm
Dr.
tilted
Barth,
like
and
I've
as he
been.
says, we just got to see his brother.
Yes.
No, I'm just kidding. We are. Scott is not here. He's in Armenia.
Armenia.
Anyways,
Going for
Armenia.
the Starmus Festival.
Yeah, it's
Lucky
going to the
dog that he
Starmus Feather.
is.
Yeah. Yeah. So it's just Dr. Barth and I today. So we're going to, I'm really excited about the topic you have. I was reading through the
Yes.
activity guide and I was like, this is pretty cool. So why don't you take it away and tell us what you're going to talk about today?
Well, thanks, Annie. I wanted to take a minute. We had some questions last time about anthropic principle. And so for those of you who are interested in strong anthropic principle, this is Frank Tipler's other book, Physics of Immortality. So if you're interested in the strong anthropic principle, this is subtitled Modern Cosmology, God and the Resurrection of the Dead. I have a very eclectic library here, Annie. You can see bits of it behind me.
Mm-hmm.
And for today's lecture, if you're interested in black holes, this is Black Holes, Time Warps, and Einstein's Outrageous Legacy by Kip Thorne with a foreword by Stephen Hawking. And that's a great book, too. So I always encourage people to sit down and read. Readeth maketh a well-rounded man. So
I have a quick
I
question.
talked to my teachers about reading, and I said, "How can you encourage young people, children, to be literate if you're not a reader?" So there you go.
Hey,
Anyway,
Dr. Barth, I have a quick
yes,
question. So how many
sure.
books do you read in a week?
Oh, I for learning and self-education, I probably read about 10 to 15 per year. And part of that is because there's a fine line between very deep mathematical treatises, which are frankly beyond me, and things which are well written enough and go in enough depth to delight me.
Mm-hmm.
And so I read, I don't know, probably 15, maybe 20 educational books a year. I read a lot of classics. I'm a particular fan of Melville, T.E. Lawrence, Shakespeare, and science fiction. I like classics. I like classic authors from sci-fi as well. Cornell and Niven, Heinlein. I love Bradbury, and I have three libraries in my house. I have this behind me is not a background. This is my office, and this is one side of the room. The other side is identical in terms of shelving, and so I have I don't know. I have probably upwards of 1,000 books here that are
cool.
Science, mathematics, engineering, astronomy. We have a second library which is science fiction, detective fiction, art, history, and stuff like that. We have probably another 500 or 600 books there. Okay. And then we have the film library downstairs, which is closing in on 5,000 titles.
That's
on
awesome.
DVD, so.
That's awesome.
Yeah.
I was just curious because every week you have a new book to show us. So I was like, I wonder how many books he reads.
I could troll through my my science library. I try to bring up things that I think people would be interested in that are still available. I have some relatively rare and classic things. Also some stuff that I'm sure is old and out of print. And over the years, I've had a number of people who have sent me, this is why Einstein is wrong. Here's my book. I have one called The New Gravity, which is particularly humorous, although not intentionally so. So I get those things in the mail every once in a while, and I keep them all. I don't throw anything out. I'm a book hoarder. I'm sorry.
No. That's good. Hey, before you get started, I want to give some shout outs to a couple of people. Beatrice Hines
Please.
is saying hello. It looks like Harold Locke has said hello. I can't see
Harold
everybody.
is bummed out about the scrubbed
The Artemis
launch. Yes.
Yes, I think a lot
That's
of us
okay.
are bummed out about that.
Launching with a malfunctioning rocket engine is a no-no, and NASA has learned this the hard way. And not just with Challenger. If you look at some of their early stuff with the Redstone and things like that. Hi, Mike. Mike's logged on. I see him. Good to see you.
Yeah.
Yeah, NASA's early stuff in the early mid-'60s was quite a demolition derby of rockets.
That's a good way to put it, actually.
Yeah, anyway. So we're going to do, promised everybody we do something easier this week. So we're going to do black hole mergers. Yay.
Yay.
And people talk about black hole mergers. They go, oh, supermassive black holes at the cores of galaxies and gobbling up everything. And black holes just seem like these deep cosmic vortexes. So they should just slurp together like magnets sticking together. But it's harder than it seems to merge two black holes. And if we think about it, we go, well, a black hole is this terrific gravity well. Wouldn't they just fall into each other? They draw in everything else and consume it. And wouldn't they just snap together? The answer turns out to be no, they don't do that. And it turns out that it's kind of an odd problem because it's relatively easy. If you want to get two black holes into the same neighborhood, it's not that hard to do. It turns out that a good number of black holes are actually born together. When we have binary star systems, and we believe that at least half, if not the majority, of stars are formed.
Oh, we lost him.
And what happens when you have two large blue giant
Barth.
stars?
You froze on us. Again. Oh,
He's still frozen.
Yeah. His internet's having a little bit of an issue.
His internet is having an issue. There he is.
Okay.
I can see you again.
Good. I'm hoping that's not like I'm looking at my internet access and it shows that I've got 5 bars. So, alrighty, we'll just go with that.
Keep going.
Anyway, to back up, it's relatively easy to get two black holes in the same region of space. And it looks like I'm freezing again, and I don't know if it's me.
Yeah.
I'm going to make sure that I've killed everything else on my computer.
Uh-oh.
Did he hang up on us?
Today,
oh, no, there he is.
And that's it.
Yeah. We've got...
okay, I think I've killed everything else.
250 up and down over here at the studios. So
okay. I could disconnect and reconnect my internet. That may help. But I'll probably have to log back on again. Shall I try that?
It's up to you. If you want to, go
ahead.
ahead.
I'm freezing again. I'm going to give it a go.
Okay, going back to Annie. Annie.
Hey, well, that's good because I was. Hang on.
I can't handle it.
You can't listen and talk at the same
I
time.
am connected now and secured, and I see Annie.
That was
fast.
Now it's frozen with a very humorous expression on your face.
That's always the best.
I don't know. I'm still spotty. Shall I try to talk without video?
It's starting to rain here in Fayetteville and Springdale, so that's probably what the issue is.
Oh, he's stuck,
stuck again.
Yeah.
Turn the microphone off on the computer.
Sorry.
Okay, I seem to be back, but intermittently. Shall I try to continue without video?
Up to you.
He's stuck again.
I'm going to try that.
Yeah, let's do that. Let's see here. Let me pull up his PowerPoint or his PDF. Cancel.
So while they're working on that, a couple of at the beginning of the month we had Sorry, I'm having to turn my microphone off, my speakers off. I can't do it. So at the beginning of the month, we had a show where it ended up being a joke how many times Scott said cool on this episode. He started saying it, and we...
I'm still only getting Annie intermittently.
At the end, we were laughing and joking about it, and so he promised that he would take a
and I should have
eyepiece.
plenty
I can't
of...
remember what size it is. I'll have to go back and look, but I have it etched to say very cool on it for whoever could guess how many.
And when I get Annie, I'm afraid I'm barely hearing
how many times
you.
he said cool, and so I finally went through it today, and we only actually had one submission for that. So anyway, so I'm just going to say Pekka Hautala is the one that answered that question, and so I'll get with Scott and we'll get that eyepiece to you, Pekka. So yeah, it's kind of funny to have to go through. I thought I was going to have to watch the whole thing over again, but luckily YouTube has this great thing called a transcript, and you do Control F and type it in. So he actually said it 40 times from the beginning of the show to the end, and so it was quite interesting to see that. But
I'm afraid,
so
Annie, I'm still getting about
I totally forgot about it until I got an email, and I was like, oh yeah, I forgot about that. So, but
are you hearing
anyways,
me?
Yeah, we are.
At this juncture?
Annie took her headphones out, so she couldn't hear you. But that wasn't because of you.
That's because. See, I'm doing it again. That's because I echo and I cannot handle it. It drives my
That's
brain
how I
insane.
operate. I hear myself talk all the time.
I can't do it.
That's what I have to do. So, Dr. Barth, are you still there? We can hear you fairly well. All right, at least we could.
Is he frozen again?
Yeah. Sadly. Let's see here. Yeah, our bandwidth is 150. So up and down.
This is the joys of having a live broadcast.
Yes.
You have internet issues sometimes. There he is.
Yes.
I see him over
So
there.
are we doing any better?
Yes, so far.
So far, okay. I'm hoping this is better. Annie still is.
Yep, you're frozen again.
I think he was just about to say I was frozen.
Yeah. Everybody out in Facebook and YouTube land, how does it look on your end? Let us know.
Are we
real quick.
frozen?
I don't think we're frozen out there. I think it's the rain and cell phone.
There he is.
Because he's using an LTE, I think.
And every once in a while I'm getting like 2 or 3 words from Paul or from Annie, and then everything freezes again.
Yeah. It's the rain. We've got a rainstorm coming in right now. That's what's going on.
Okay.
So do you want to try to keep going?
If you can hear me, I can keep going without feedback.
Yes.
That's perfect.
We
To
cannot
rooms full of
always hear you,
students who
though.
stare silently and don't give me feedback. So,
We could
all
try.
right. All right, we'll try this. So we're going to start from the top. And black hole merging is more difficult than it seems. It turns out that although we would think black holes would snap together like magnets, that they do not in fact do this. That it's easy to get black holes into the same neighborhood, one from another, but getting them to connect is much more difficult. It turns out that pairs of black holes are often formed in binary star systems. When we have a binary system with a couple of very large blue stars, They will burn out and supernova into a black hole end state, one after the other. And you would think that a supernova that close would just blow the star out like a candle, but in fact, it doesn't do that. So we often get paired black holes from binary systems, their end evolutionary state. And these stars can be anywhere from a few AU to a few thousand AU apart. Their orbital periods can take anywhere from a few hours to tens of thousands of years. And when we look at these two pairs of black holes, we realize that they're not necessarily both the same size. And because of that, they don't precisely, people have this idea of two black holes orbiting around a center point between them. But that's not true, and I'm going to try to give us a little demonstration here. I have I'm going to ruin, well, this pen is just about empty anyway. I'm going to put two different sized balls of clay, one on each end of the pen, and you can see that these two will balance. There we go. These two balance, but not precisely at a center point. This balance point between them is called the barycenter. And in fact, if they were orbiting in space, see if I can do this, they would orbit around this barycenter point. And the large one makes a much smaller circle than the smaller one does. This happens with the Earth and the Moon, but the barycenter between the Earth and Moon is buried deep within the Earth. It happens for the Earth and the Sun. Same thing there. The Sun outweighs the Earth by 1,000,000 times or thereabouts. So the barycenter is deep near the core of the Sun. The Pluto-Charon system is a binary planet in truth, because the barycenter between Pluto and Charon is actually out in space between them. So that's interesting. And these binary systems tend to have larger and more elliptical orbits. And the exact nature of the orbit will depend upon their relative masses. If they're very close, magnetic fields can interfere and change the orbit. But these things don't like to merge. And you think, well, why not? We know that moons spiral in towards giant planets and are torn apart. That's how Saturn and Jupiter formed their rings. Moons actually spiraled in, they were ripped apart, and we have a program about that, about gravitational disruption and rings. And so what did happen with black holes? Well, oftentimes friction is what's the problem. And you think about, oh, well, if a black hole was in a cloud of dust or gaseous material, wouldn't it experience friction? Not in the conventional sense. If they run into something, when your car goes through the air, you have to push air molecules out of the way. Black hole simply absorbs the things in its way. So no friction in a conventional sense. And we know that merging two black holes is possible. We know that it's possible because, first of all, almost every galaxy that's close enough that we can detect, almost every galaxy has a supermassive black hole in the center. We know that the Milky Way does. We call it Sagittarius A star. We know that some galaxies have none, but that's relatively rare. Triangulum, which is M33, has, as far as we can tell, no supermassive black hole. If it has a central black hole, studies indicate that it's less than 3,000 solar masses for a galaxy central black hole that's teeny tiny. And we know that once in a while, galaxies have two black holes. Andromeda actually has two supermassive black holes. And in both these cases, the galaxy with none and the galaxy with two, we are pretty sure that what's going on there is a galaxy collision. Smaller collides with a larger, and the larger one says, I'll have that, thanks. And like a pickpocket, steals away the supermassive black hole from its companion. And we're pretty sure that's what happened with Andromeda and Triangulum, M31 and M33. And both of these galaxies show evidence of cosmically recent collision. let's keep an idea that what we mean by cosmically recent is in the last, 3 to 5 billion years or so. So we know that regular interactions, collisions, mergers of galaxies, and we know that the lack of galaxies with a supermassive black hole system tells us that black holes can and do merge. We believe that's how galaxies form a supermassive black hole in the first place. The other evidence we have for black hole mergers is from observatories like LIGO and Virgo, which are the gravitational wave observatories. And with these observatories, we can detect gravitational waves. And merging black holes have a particular signature, which includes a gravity wave chirp as the merging finishes. So if we know they merge, why do we think that merging modest black holes, stellar-sized black holes, is so difficult? And the post office and Amazon both understand this. It's called the last mile problem. For black holes, astronomers, and I've seen this in various science writing. I don't know if there's a legit astrophysicist who uses this term, but they refer to it as the last parsec problem. Hello, Parker. That's my service dog pal, Parker, who's wandered on screen with me. Anyway, if you want to merge two things that are orbiting around each other, you need to get rid of angular momentum. To give you an idea what it means to redistribute angular momentum, if you see an Olympic skater who is spinning with their arms wide flung, and then they wrap their arms tightly and their rate of spin goes way up, what you're seeing there is actually the conservation of angular momentum. When we draw the mass in more tightly, we speed up the rotational rate. When we distribute the mass more widely, we slow it down, but the angular momentum remains constant. But to get things to spiral into each other, we need to actually get rid of angular momentum. And angular momentum is really, a typo in my notes there, says two things. It's actually three: mass, velocity, and radius. So we think of how heavy is something, how rapidly is it rotating about the center, the barycenter in the case of a couple of black holes, and what's the radius? We used to do experiments like this in physics class where we would have a solid disk and a hollow ring, and they both weighed the same, and we would roll them down, and we would see they would roll down at different speeds. Why? The ring has greater angular inertia than the disk, and so it spins up more slowly. You may have seen the classic gyroscope, which is a ring of metal on an axis, and you spin it up with a string, and it exhibits a lot of angular momentum, and so it will balance on the end of your finger and that sort of thing. If we think about these three things, mass, radius, velocity, radius can be anything you like, from literally almost merged just a few light seconds away to, 10,000 AU, and it takes 100,000 years to go around once. So radius can be anything, but when you're talking about black holes, the mass is always big, right? You're talking the Chandrasekhar limit, something like 2.4 solar masses and up. That's a very large thing to have packed into a very small space. And the velocity, as the black holes move together, if you decrease the radius of the orbit, you increase the velocity. This is classic Kepler's law of planetary motion, and this is why Mercury goes around in basically 3 months, where about twice as far away, the Earth takes a whole year, and you go 5 times farther away from the Earth. Instead of 1 year, Jupiter takes 12, and so on. And so this Keplerian law says as things get closer, they orbit much more rapidly. And so we look at this, how do we get rid of angular momentum? Black holes are among the most massive compact objects known. And they have tremendous amounts of angular momentum. And as we mentioned, you can't get rid of it with friction. Elon Musk knows all about loss of angular momentum and friction. A few months ago, he lost something like 44 Starlink satellites because the sun was unusually active and boosted out the exosphere to be a little bit larger, and so his satellites were actually orbiting in the exosphere instead of out in space proper, and so there was too much drag, and so he had a couple dozen satellites deorbit and burn up. My, that was expensive. That's worse than your Tesla's battery catching on fire. And so we know this. You may remember Space Lab, the America's first working space station. Skylab, that's it. And the Skylab eventually, they couldn't maintain the orbit, and it encountered too much friction with the upper atmosphere, and it burnt up and deorbited. And we see this with satellites all the time. And it's not happy when a big satellite. There was a bunch of fuss because the Chinese deorbited a big satellite recently. And it was like, well, they didn't have a lot of quality control on their reentry program. And so nobody was quite sure where it was going to land. And if they knew, they weren't talking. And, we'll just deorbit it over the outback. Well, that's fine unless you live there or unless they make a tiny miscalculation. And there's a very large section of the southern Pacific, which is actually a satellite graveyard. And but black holes aren't subject to friction like normal things. Normal things, friction is when we rub against. But if you try to cozy up and rub against a black hole, you just get absorbed and incorporated. So you think about you see these wind tunnel tests, right, where they show the smoke streams going over the top of a car or whatever. The car is made of black hole material. Basically, the smoke streamers are just going to be absorbed completely, and there's going to be nothing on the other side. So friction isn't really an option. Well, what about gravitational waves? Ooh, can't we use gravitational waves? These indeed carry away energy, and it's one of just two ways that black holes lose energy and mass. The other way is the famous Hawking radiation, and we will save that for another time because that's another topic. But Hawking radiation, the radiation escapes from the black hole, and as the radiation escapes, E equals mc squared, Einstein rules, you have to pay for that. You have to pay for that energy with a tiny amount of mass. And so when a black hole evaporates, how long does it take for a stellar mass black hole to evaporate? Freeman Dyson, the astrophysicist, once estimated it takes 10 to the 80th to the 100th power. So a 10 with 80 to the 100th power zeros. I can't even mention. That breaks the shock absorbers on my brain. Sorry. And you also find that the ratio of gravitational strength to electromagnetic strength is 10 to the 40th. And yes, that's one of Dirac's large number coincidences, the large number theory. And so I wrote down there for you what 10 to the 40th looks like. And it's just hard. It's very hard to understand. So Dirac spewed a bunch of zeros again, but he never cleans those up. 10 to the 40 is one of those numbers that occurs too frequently in nature to be coincidence, probably. And we think that many astrophysicists, including me, believe that this number 10 to the 40th is a function of how old the universe is. So this gravitation being 40 orders of magnitude weaker. So you take that gravitation, the 10 to the 40th, and you make it a TH, right, instead of 7/1/7, right? So 10 to the 40th as a fraction is very, very small. And because of that, gravitational waves just don't carry away significant amounts of energy compared to the massive angular momentum or angular kinetic energy, if you will, that an orbiting black hole has. So people said, all right, well, you can't have friction, you can't have gravitational waves carrying away much of the angular momentum. Does that mean that pairs of black holes or black holes in a multiple system are just forever? No, it turns out not. It turns out that if you have a third companion, and if you have a massive object orbiting well outside the orbit of the binary pair, that it can change the orbit of the binary pair and make it more elliptical. And it turns out, people say, oh, can you really have a trinary with a black hole? Well, yes. Trinary and higher order multiple star systems do exist. And I put up a diagram there of Pollux from the Gemini constellation, Castor and Pollux. And it turns out Pollux is a 6-star system. And it's very, very strange. There are 2 inner binary pairs that are in very close orbits, and these pairs orbit around each other, and then way out, occupying something like a 20,000-year-long orbit, there's another binary pair, and astrophysicists look at this Pollux system, and I have not seen anyone come up with a feasible origin for how this happened. Pollux, what the heck? It's just a very, very strange system. But the third companion, and there's another graphic there. You can take a look at the idea of the third companion. And what the third companion does is it distorts the orbit of the other 2. There we go. Thank you, Paul. So we see our pair of 2 orbiting binary black holes. And the barycenter point is there, a little blue star, where they're orbiting around. And yes, I'm simplifying here. I didn't show both black holes orbiting in their own circles. I just said, well, we're just going to draw it as...
Do we need some sinister music?
Some sinister music? Yes, Henry Mancini's Experiment in Terror. I'm sure we're not licensed for that, but folks, if you want to look it up on YouTube, that would be the music I was thinking of. Henry Mancini and Experiment in Terror.
Facebook recently has tagged Scott talking with no sound as copyright infringement. So it's who knows what's going on with that.
Yeah, I don't know. They sent me an email saying some of your videos can no longer be seen with sound, but we generally don't play sound. Once in a while, we have an ESA or a NASA video that has their own music, but it's public domain from them, and we assume they're not plagiarizing anybody's musical work.
Yeah, it's
I'm sure people would line up to say, "Here, NASA, use mine." Yeah. But we can see our third companion lurking there far outside the orbit of the other 2. And what happens is this third companion will stretch the orbit of the other pair of binary black holes and make it more elliptical. Well, what difference does that make? The difference that makes is when the orbit becomes very elliptical, that once every orbit, the 2 black holes are in a lot greater proximity to each other than most of the time. Think of a comet orbit here, like Halley. Halley orbits once every, 76 years, give or take? And so as it goes around, Halley, for a short time, is very close to the sun, and it outgasses, and it's beautiful, and then it dives out into the outer solar system again, and no more cometary tale for us to enjoy. Well, these black holes are doing something of the same thing, but instead of having a cometary tail, what we're having here is the two black holes get close together, and this allows gravitational waves to do more work. The closer you are, the more gravitational energy you shed in the form of gravitational waves. And it turns out, yeah, okay, the trinary system has to be pretty finely tuned for this to work. And we found out last couple of weeks that a finely tuned universe is not as randomly odd as it sounds. Is there some mechanism for tuning the orbits of black holes with third companions? I was unable to find any in a literature search. However, we do know that depending on which black hole gravitational wave survey you look at, we estimate something between 15 and 38 black hole mergers per cubic gigaparsec every year. 38 mergers in that much space, a gigaparsec, a cubic gigaparsec no less, is that's a lot. That's a lot. Gigaparsec is on the order of galactic volume. And I'm just shooting from the hip here. I would have to get out my calculator or a slide rule and do some serious math. But when we say, oh, trinary systems have to be in a very precise arrangement. They have to be at the right distance so that the frequency, the period of them going around matches how they interact their orbital period with their third massive companion. And you're like, gosh, how would that work? How could you even tune that? How could you affect that? And it turns out that this isn't as big a problem as you think. First of all, trinary black hole systems are just plain old trinary systems are not common enough to get even half of the lowest estimate. In other words, with our 15 to 38 per cubic gigaparsec, regular trinary black holes systems couldn't be more than about 5 to 7 of these mergers per year. And so you're like, well, it turns out supermassive black holes, or SMBHs, right? We're wandering into dangerous territory here already. So I don't know. You can't unhear this. So I'm going to do a rap for you. I thought I would get out my big gold chain, and then I realized I don't have one. And I could bring Parker in because he's my big, black, ferocious-looking Labrador dog until he, just decides to climb in somebody's lap and shower them with kisses. So I'm calling on all of my SMBHs, warping your space in your hot central regions. You gotta pick up the slack from your trinary legions, making your holes do the merger so we can see them. Yo, holes. So there you go. Yay. I know, that was awful. And you're too far away to throw rotten fruit and tomatoes. So I feel safe in inflicting you with this.
Hey, before we skip on, before we keep going, Osmosis 007 asked if black holes ever merged, would we even be able to see it? As the mass increases, doesn't the relative time slow down for the observer versus the object? And then he makes a joke about could have read too much science fiction.
No, good for you. Good for you, Osmosis. Can you see it? Black holes, unlike neutron stars, unlike regular merging objects where we get a flash of light, a couple of pulsars merge or a couple of neutron stars merge, we get a lot of visible and ultraviolet radiation. Black holes, it's unclear. It's unclear, but not very much, because remember, they trap everything, even light. So how could they generate light we could see? Well, one way is if they were shrouded in a disk. And black holes do have accretion disks. We know this. Some black holes, especially supermassive black holes, my SMBHs, they do have some of them large accretion disks, and we know that active galactic nuclei or quasars, these are young galaxies where the central SMBH has a large, dense accretion disk and is swallowing up many solar masses of material at the time, and that accretion disk, as it's compressed, as it's spun up from the black hole, frame dragging of the space-time around the black hole, this stuff gets compressed, friction, a lot of heat is generated, and these accretion disks radiate in X-rays. This is how the very first black hole that was confirmed, Cygnus X1, was an X-ray source. And it was finally confirmed to be a black hole surrounded by an accretion disk. And it's the accretion disk which is glowing. Mike Overacker says gravitational waves would be produced. Oh, yes. A tremendous amount of energy in gravitational waves. And that's most of the radiation that's emitted from a black hole merger. So it turns out, we think of this trinary problem. Well, what if the really big black hole that's far away from your tight binary pair, what if that's a galactic central supermassive black hole? Well, could you get it to line up? Could you get it to work? It turns out that you can. And we say, to effectively stretch the orbit of the close binary pair to make it very elliptical and therefore make it more likely for a merger to occur, it turns out that you have to have an orbital period for the two, which is synchronous with their orbit around their third companion. Well, if we think about objects near an SMBH in the center of a galaxy, everything migrates inward, right? Here we have a gigasolar mass black hole. Surprise, everything migrates inward. It just does. It has no option. The black hole is relentless, frame dragging, friction with the accretion disk. It's like one of the dead satellites which meets the upper atmosphere. The black hole relentlessly draws everything inward. So it turns out that the binary system has to precess. And if we think about precession, that's where the Earth's orbit of axis changes and it rotates around over time. And the precession must synchronize with the orbit around the large companion. And you go, okay, well, all orbital systems precess. It's possible to have a perfect orbital system that doesn't, but the first time anything perturbs it, it's going to start precessing. This is like the idea of a perfectly circular orbit. Can you have a perfectly circular orbit? Yes, but it's one of literally an infinitude of probabilities, all of the rest of which are elliptical. So even if you have a perfectly circular orbit, the first time anything disturbs it, it becomes an ellipse. Well, so binary systems must precess. And because these binary pairs are gradually migrating inward toward the black hole, they are going to reach a point where their precession matches their orbital period around the supermassive black hole. And you can think of this, the precession rate is fixed over time, but it is the migration inward, and there will be a place where it matches. The migration is relatively slow, but the universe has a lot of time, and so as these things migrate in, they're going to reach that magic point where the precession rate is now equal to the orbital period, and once that happens, things start happening relatively quickly. The orbit of the binary pair becomes stretched extremely so, and now the smaller black hole is orbiting around the larger one in the binary pair, and it's like a comet. It's like a sun-grazing comet. It's now coming closer every time. And so as these binary pairs migrate inward toward a supermassive companion or a supermassive black hole in the center of a galaxy, as this binary pair marches inward, it eventually it must reach a place where the rate of its precession and the rate of its orbit around the supermassive black hole will match. And once it hits that, you have a sort of a resonance which occurs. And when this happens, the black holes merge relatively quickly. Again, we're talking cosmic timescales here. And the black holes merge, and then the binary pair is no more. So we have this interesting thing, and as we're looking at detections with the LIGO and Virgo observatories and others that are supposed to come online, and we're looking at observatories which look in the X-ray and like Chandra, and what we're doing is we're taking data from all these observatories and we're putting them together. LIGO and Virgo detect a gravitational wave event, and scientists immediately go back to the record from places, telescopes like Webb and Hubble and ALMA, the Atacama Large Millimeter Array. And we look at these and we go, oh, let's look and see if we happen to capture at that place in the sky, was there an optical event or an X-ray event or a microwave event, which syncs up both in location and in time with our gravitational wave event. And we're finding some success. But at the time, the number of gravitational wave detections from black hole mergers is very small, in a dozen or two. And the technology for this only came online less than a decade ago. And we look at this, I think the first successful gravitational wave detection was just in the last decade or so here. And so this science is really in its infancy, which is very exciting, because we are now, friends, if you are a black hole fan and you love my SMBHs and the binary pairs and the trinary pairs and the mergers and the idea that, wow, this is great, this is cool, you are seeing this at the infancy of the science. This is like being on the roof with Galileo and some of the cardinals. Look, Jupiter has moons. It can be frustrating, because we say, oh, when do we get more data? When do we get to know? But the very nature of science is that sometimes we don't get to know really quickly. And this, I think, is a NASA simulation here, or an ESA possibly. What I'm doing to my students, and I use that term advisedly, doing to my students this semester, see if I can find, I know where it is, hang on. Here we go. Digging into my student folder. This is what the activity I'm having my students do right now. And I'll make the connection here in a second. I think we can see this. Yes, this is the Lunar Phase Challenge. What I tell my students, okay, I tell them, here's what the moon, I'm at the other end. Here's what the moon looks like tonight. And we're just at the start of a waxing phase. So I give them the thin little crust and I say, here's what the moon looks like tonight. Now in ink, please, go across these four and predict for me how you think the moon will appear every 2 to 3 days over the next roughly 10 to 12 nights. And they do it in ink. And then they say, well, how long will it take us to figure this out? Well, the waxing moon takes 2 weeks. And I had them first day, make a lunar phase diagram out of clay. And they said, is it correct? And I said, I don't know. They said, well, how can you not know? I said, well, I haven't observed the moon yet. Well, how long will this take? Well, to see if your entire phase diagram is correct, it takes a month. They're like, a month? And they're stunned because their science teachers lie to them. Mm-hmm. And I said, how many of you had every single science experiment you had finished in a 55-minute period? Most of them raised their hand. I said, okay, did some of you have a thing where you plant a bean seed and measure the sprout over a few days' time? Yes. Or watch a tadpole turn into a frog or a chrysalis and a butterfly emerges over a couple of weeks. But those are kind of like, look at these events. I said, but you know what? The sky is our laboratory, but we don't control it. And they kind of have this, television detective mystery where we always catch the bad guy by the end of the hour program. They said, oh, science isn't like that. Some of this stuff takes time. In some cases, decades. So over the rest of my lifetime, which I hope will be some decades, cross fingers, bonk, bonk, knock wood, I will get to see how this science evolves. But certainly our children will. Mm-hmm. And we look at this and we say, well, what do we know right now? But we have to put the little asterisk on there. It's like one of those baseball records during the steroid era. There's a little asterisk here. 75 home runs, asterisk, steroids. Well, guess what? The stuff we know now may in fact be overturned and refuted in the coming decades. Scott and I have both talked about how things we were taught as boys in school that were not true. The moon did not form when proto-Earth spun too fast and a chunk simply tore away. We didn't have a proto-Earth here and a chunk split off and became the moon. We didn't have, that's not how it works, but that's what we were taught. And Apollo put that theory out with the trash. No, it doesn't work that way. Well, the current theories we have about merging black holes and how they merge and how supermassive black holes have a role here, with Webb and Chandra and the new supermassive telescopes which should be coming online in the next 10 years, like the extremely large telescope and the TMMT, the 30-meter telescope. A lot of these mega projects which will be coming online in the next decade or so, they may change our theories entirely. They may basically say, well, sorry, what y'all thought 10 years ago, nobody believes that anymore. So we're going to have to wait and see. And that's part of what makes being actively involved in a changing, developing, growing science so important and so exciting. So there we go for this week. Annie, do we have any fun questions?
No, everybody's just kind of been making comments. Mike Overacker says, lots Oz. Man, this black hole talk sucks. I think you put
I knew I could count on somebody to make that joke.
And then he also says, heck, a bunch of my questions I will never live to know the answers to. But, that's so true. That's the great thing that I'm learning by coming onto your show is that, science is ever changing. We're always learning and evolving evolving and learning new things. And so what's new today might not be new in the next few years. Something can change.
There we go.
Ideas and stuff, so like that. So.
But it's really great to go ahead and get out with your own telescope or binocular. I just read about an astronomer, I think it was Roger Alcock, and he was a British fellow, and he discovered more supernovas independently than anybody else, and he discovered dozens of supernovas and many comets and asteroids, and he did all this with a pair of 15 by 80 binoculars.
That's crazy.
Which in the late 1950s, early 60s was some of the wow, whiz bang, best equipment you've got. And I know a lot of people, and I hear this every once in a while, because somebody says, well, what kind of telescope should I get? And to this day, I recommend a 6 to 8 inch Dobsonian. It's simple, it's rugged, it's easy to use, and it can last you for a lifetime. Well, you can't see anything good with that. Oh my gosh, you know how much history was made with telescopes smaller than that? Mm-hmm. Yes, you can. You can easily track down 10,000 or more targets with a 8-inch Dobsonian in your backyard, and you don't need computer equipment. And I encourage everybody, participate in the discovery. Oh, this is the hardest part of astronomy outreach. Keeping up with all the new info is a constant effort. Yes, I have people ask me, Annie, how I get people to come out to my evening astronomy labs, and part of the secret for the first astronomy activity night of the year I generally have a giant taco feast. I made
Free food.
expecting 40.
Free food
Expecting
and
40
cash.
this year, free food. So
Yeah.
I made 12 pounds of taco meat, and I provide the cheese and the chopped onions and diced tomatoes and lettuce, and the kids bring out the taco shells, the chips, salsa, soft drinks, and we provide the paper plates and cups. And so everybody comes out to my ranch, and we have a giant taco feed, and then we go out and look at the Milky Way and look at the
Dr.
waxing
Barth.
moons.
Dr. Barth, next time you have a taco feast, make sure my email is included in the directions.
Wednesday night, arrive between 6:30 and 7 o'clock. If you want directions to world famous Barthland Ranch and Observatory, I will happily email them to you and Annie, because that's cool stuff. And I'll have you know, I'm hoping I can get this up right now.
You can hear the rain. It's raining so hard.
It's storming
here
really bad here.
in Springdale.
Oh, we don't have any yet. I'm
Here in
looking
Springdale, if you're listening, when you listen back, because you probably can't hear it, that's rain hitting the building. It's that hard.
And I will share this with you. I think we can share this. We're going to try this. This was last week. I had an impromptu lab night. It wasn't supposed to be clear what it was. I had about half a dozen students come out. It was a brilliant night. And this is me with an LED. You can see that I am in waxing gibbous phase right there, in my baldness. And I'm there with a student's cell phone because they had better reception than I did, and an LED light, and I'm on the Global Star Party live with my students. So it's all happening. But no, I would be seriously though, I would be thrilled to have you and Annie come out as guests and show up to my astronomy night. So I will go ahead and I will I will send you information to contact me with my remind, because I send out a remind bulletin. And a perfect chance to test the water resistance of Explorer scientific telescopes. No, please don't. Please, if you can use your Dobsonian as a light bucket, please, but not a rain bucket. But no, I'll put you. I'll have you sign up for my remind, because I usually send out a last minute. Is the sky really, really clear? And be happy to have both of you out. So
That'd be
if you
awesome.
are free, come out as my guests and attend one of my astronomy nights, and you can take some pictures and put them up on the Explorer website or whatever.
So let's not
It's lots of
forget
fun.
about your book, Dr. Barth.
That's true. So if you all are out and you are wondering what to do with your telescope and how to participate in our exciting adventure of astronomy, Star Mentor, hands-on projects, lessons in observational astronomy. So this isn't about astrophotography. It isn't about giant equipment. This book assumes you have something like an 80 millimeter refractor or a 6-inch dot. Truly modest equipment. And if you've got bigger, fancier equipment than that, but this book is designed to help you learn how to navigate the sky, how to navigate through the sky with your telescope, how to learn about constellations, how to learn about what you are seeing. A lot of people say, if you go out on astronomy outreach, Mike Overacker can, and Mike Wiesner, I'm sure, and some of the others, Harold Locke and Becca Harkala can back me up on this. People walk up to your telescope, can I have a go? Sure. And they put their eye up to it, and you're looking at Andromeda, you're looking at the Hercules cluster, you're looking at the southern Milky Way, and they put their eye up and say, okay, what am I looking at? And they're not being facetious.
Yeah.
They're bringing zero knowledge to the eyepiece. When you take a book like Star Mentor and you start working through some of the exercises, you're actually bringing more knowledge to the eyepiece, which means you're going to build up not only your skills, but your enthusiasm. And when somebody else comes up to you, and they will, wow, you have a telescope? Can I have a go? I want to try. I've always wanted to look through a real telescope. And you've got your 6-inch Dob, and they go, wow, that's enormous. and you grin at them because you've seen some of these 25-inch obsession Dobsonians and the 8 and 10-inch refractors, and you grin when they say your telescope is tremendous. And when they say, "What am I looking at? Teach me, help me learn." The Star Mentor book is your guide. Both you're getting a chance to go observing with me by proxy, and it's a way to help you learn to be an effective outreach astronomer and bring the joy of working with a telescope in your backyard to more people. So, and we're still looking for reviews. So if you haven't got the book, good golly, Springer.com or Amazon.com. That's available from fine booksellers worldwide, because Springer is an international company, and I would be thrilled to see some reviews coming in on Amazon or Springer. So there we go. And next week, we'll figure out something fun to do. I think we're going to take a shot at circumplanetary disks. This is what I did for the Global Star Party, and I just barely scratched the surface. And it's something that we've been talk about. When will we know? Well, we've been thinking about circumplanetary disks for at least 50 years. We finally found one this summer. And so the ALMA Large Millimeter Array finally detected one, which is exciting. And so next week we're going to talk about circumplanetary disks and how moons form. So that'll be next week's program, and I'll look forward to sharing it with everyone.
Hey, so I just want to real fast talk about this week, what we have going on this week. Great yes. talk, Dr. Barth. That was amazing. So tomorrow we're going to have Education Through Learning on Amazon Live, and then it's going to be the Global Star Party is not going to be happening because Scott is out of town. And then Wednesday will be, again, our Amazon Live. We have those every day at 3:30. I'm sorry, at 3 o'clock. Sorry, misspoke. But Kent will be back with us with First Light Chronicles in the afternoon. And then Thursday will be Explore Alliance Minutes. And then Friday will be focused on astrophotography. Tyler will be back, and I'm really excited to hear his talk on how it went in Texas. He went to do an astrophotography class up there. So join us throughout the week, and we will see you guys in the chat. Have a great day.
Outstanding. Bye-bye, everybody.
Bye.